Hi, hello everyone. So this is the video dealing with section 3.4, exponential and logarithmic equations. So this is a review for the topics that were covered in Math 119. So it's exactly the same topic we review here uh, for the need to be able to solve application problems now or later. So I've divided this topic into two videos. The first part is solving the exponential equations, and the other one will deal with solving logarithmic equations. Okay, so a exponential equation is any equation where the variable is in the exponent. Okay, it could be just a single x, 2x, 3x, 4x, x squared, and so on and so forth. So there's three we normally show students the three types of exponential equations that you can see. They're very easy to solve. The first case is the most basic of them all. I'm going to call it A. This is where you have an equation where the bases that you see are the same. Okay, so for example, here's 3 to the x, and here's 3 to the 2x plus 1. By the way, let's just remind you of these things are. So for example, 3 to the x. This number is called the base, and this number is called the exponent, which in this case now here is represented by a variable. Okay. So first case, you have an equation where both bases are the same. This is very easy, and I'll show you exactly how to do it. Equations where you have different bases, but they can be made the same. All right, so let's take a look. Left side of the equation, I have a base 3. Right side of the equation, I have the number 81. But it's possible to rewrite 81 as 3 to the 4th. And now the two bases are the same, and I'm back to case A. And then you have the third type of equation where the bases are different and they cannot be made the same. For example, 3 to the x and 12. All right, so I cannot turn 12 into something with a 3 to an exponent. Or for example, 3 to the x equals 4 to the 2x. Right, so it's not possible to make them the same. So there's a specific technique for this. And the first and second case are pretty much the same technique. Now, your textbook covers the technique for you to solve exponential equations in a specific way. So first, we isolate the exponential expression into one side of the equation. In our case, we're always going to isolate the expression on the left side. Then the textbook suggests that you either take the log of both sides, base 10, or base E. Okay? We are going to do, so this is specifically for the last case. Okay? The first two cases, A and B, have a very, very simple technique. And the third case, they suggest you take the log of both sides, either base 10 or base E. Now, I'm going to show you a different technique that works better than that. Okay? All right, so let's take a look at the examples I have for you. Now, these examples cover every single topic, every single type of these exponential equations. So this is going to be type A, where both bases are the same. This is going to be type B, where the bases are different, but they can be made the same. And then the last two cases, example 3 and example 4, taken from your textbook, are cases of type C where they cannot be made the same. So this is pretty much everything. So if we're able to do these problems, then we should be fine. Now, also keep in mind again that this is a review. We had this in Math 119. So we're hoping that this is not a major issue for anyone. Okay, so I'm going to start solving the first two cases. Just make it a little smaller so I can write it on the right. Okay, so this is the first one, and this is going to be the first type of a problem where the bases are exactly the same. Okay, so when the bases are exactly the same, then all we need to do is there's the step inside that you don't see it, which is we take the log base 2 of both sides in this case, because the base is 2. You have to make sure that you start with each log expression, I'm sorry, the exponential expression isolated on its side, all right? I cannot have more than one exponential expression on each side. So in this case, they're both isolated on the left and the right, so I can start the process. If I had a situation like this, for example, right, I would have to move this to the other side, right? So I cannot start the problem in this format. So each exponential expression has to be isolated on its own side. All right, in this case, they are. So now we would take the log of this base of both sides. And when we do, this is what happens. I'm only going to show you the one on the left. Okay, now, but the properties of logs, this exponent goes in front of the log. And then I have this. And then I apply the properties of log again, and log 2 base 2 is just 1. So then I have 3x plus 5 times 1, which is obviously just 3x plus 5. Okay? So because of this, when the expression or the equation has the same base, what we tell the students to do is just cancel the base. So you end up with, this is only possible if the bases are the same, equal x minus 1. So now you're left with solving this linear equation. And you know how to solve this linear equation, minus x on both sides. Minus 5 on both sides. Divide everything by 2. And we're done. Okay? So if the bases are the same, just cancel the bases due to the taking the log of that base of both sides and simplifying using log properties. So that's fairly easy. All right, so this is the first one, first type. Second type. In the event the bases are not the same, but they can be made the same. Okay, so again, we make sure that each exponential expression is isolated on its side, otherwise we cannot begin. And we look at the bases, 3 and 9, they're not the same, but I can rewrite 9 so that the bases are the same. So how do I rewrite 9? Well, I write it as 3 squared. So I'm going to replace 9 with 3 squared. 3 squared, parentheses, minus 2x plus 1. Okay? Now, look what happens. The bases are the same. So just as before, this becomes a type A problem. They cancel. I am left with just the exponents. And again, this becomes a linear equation. I will distribute it to, and I'll solve this now, right? All of the x's to the left, add 4x to both sides. Add 6 to both sides. And divide everything by 6. So out. Whoops. And then simplify the fraction, right? By 2. Okay, so my final answer is 4/3. So this is type 2 in the event that the bases can be made the same, then we should do so, right? 3 and 9 can be made the same with this conversion right here. All right, so these two are the very basic two types. This technique works fantastically well. It's very simple. It'll turn the equation into a linear equation, which is most cases, and in some odd cases, a quadratic equation, but I don't think you'll see that, just linear equation. Okay, now let's take a look at the next two cases, which is probably the most important, where the bases cannot be made the same. So this is where we have to employ the log technique. So here's the equation. I'm going to write it here. So these two are type C, right? Where they cannot be made the same. So 40E 0.6x minus 3 equals 237. All right, so this is what we have. Let's just make sure that we write this thing. 0.6x. Okay. Now, step one, as before, we need to isolate the expression where we have the base. So here's the expression where I have the base. Okay. Where the exponent is. I have to isolate this expression. So the negative 3 cannot be here. So I'm going to add 3 to both sides. All right. Okay. So now it's isolated. So we begin the process. So the very first thing I have to do is I have to divide both sides because this number cannot be here. So I have to divide both sides by 40. And that is 6. It's easy enough. Okay, so now this is really our starting point where I have a base. I have just the number 1 multiplying here. I have an exponent. I have something on the side, on the other side. Now, this base cannot be made the same to the number 6 or vice versa. So what do I do? So this is the technique. So your textbook says to take the log, either the natural log or log base 10 of both sides. I am going to say, and you're going to see this in example 4, I am going to say the following. Whatever this base is, where your variable is attached to, you're going to take the log of both sides using this base, whatever it is. In this case, it's E, so we'll take natural log of both sides. If it was 7 to the x, you would take log 7 of both sides. If it was log 17, you would take log 17 of both sides, and so on and so forth. Okay? In this case, it is base E. So we'll take natural log or log base E of both sides, and you see why in a minute. Now, by the properties of log, the whole exponent goes in front of the log. Now, again, this is a review from Math 119. In case you forgot the properties of logs, just go review, take a look at a couple of YouTube videos dealing with properties of logs, and you remember how to solve these things. So 0.6x times ln e ln 6. Now, again, by the properties of logs, natural log of e, which is just log e base e, right? It's just 1. Just like we've seen before, log base 2 of 2 is 1. So this is just 1. So it's 1 times 0.6, which is just 0.6x. So that's the reason why we take the log of this base, because it'll cancel completely. All right? This is exactly what we want. Natural log 6. And now we just divide both sides by 0.6. And my answer is natural log 6 divided by 0.6. If you want, you can evaluate this using the calculator. I'll do it here for your benefit, but it's not necessary. So I'm going to do it here. I don't know if you're going to see it on the video. I think you will. So natural log 6, and here's the natural log 6 divided by 0.6, and we get this answer, approximately 2.98. And there you go. This is my answer. Okay. So in the event you cannot convert the bases like we had over here, right? We are going to take the log using the base where your variable is of both sides. All right, let's see the last and final case where now we have the situation where it's visibly clear from the beginning that you cannot convert the bases. Okay, so now both exponential expressions are isolated on their side, and obviously I cannot convert, 4 to 5 or 5 to 4. So what do? You will take the log of both sides using one of these two bases. Just like before, remember we had e to the 0.6 equals 6. In the previous example, I only had x in one side, so I needed to take log base e. If I had an x right here too, then I have a decision. I can either take log base e of both sides, or I can take log base 6 of both sides. It doesn't really matter. You pick one, and the answer is going to be the same. So here's an example, the last example, and we have two bases, and I have variables in both of them. So you can either take log base 5 of both sides or log base 4. It does not matter. Your textbook says take log base 10, but that's worse. That is very, very much, much worse. You take either log base 5 or log base 4, and you see why. I am going to take log base 5. And you see what happens. Okay, so whatever you do to one side, you have to do to the other. Okay, don't take log base 5 on the left and log base 4 on the right, because it will be incorrect. Okay, now let's take a look at the left side. By the properties of logs, this goes in front of the log right here. And now I have this expression log base 5 of 5, which is what? This is 1, just as before. So I'm going to have x minus 2 times 1, which is just x minus 2. That's why I am telling you to take the log using this number or this of both sides instead of log base 10. Did log base 10, this wouldn't work this way. On the right side, I have something similar that happens. This goes in front of the log. Okay, I just have log 4 base 5. Okay, so now I have to distribute this expression right here. I have 2x, and I'm going to have to figure it out what this thing is in a minute. Okay, but I don't want to be handling or dealing with this ugly looking expression. So I'm going to do this. I'm going to say let k equals log base 5 of 4. Okay, so I'm going to call this k. So now once I distribute to x, I'm going to get 2xk plus 3k. Solving this for x, right? So I'm going to subtract minus 2xk on both sides. And here I have x minus 2xk minus 2 equals 3k. I'm going to add 2 to both sides. So now I have to find out what this is. So I'm going to go to the calculator and I'm going to evaluate this. Now, your calculator may not do this because it doesn't have a base 5, but we have the change base formula, which says the following. When I have log base b of a, I can do log base 10 of a, log base 10 of b. So this is exactly what I'm going to do. So this expression here is log base 10 of 4, log base 10 of 5. Now, remember that when it's log base 10, I don't have to explicitly write the base. I am writing here because I don't know if you remember all of the details of logs. So I'm going to do this on the calculator, and I'm going to find out what the answer is. All right, so log 4. Notice how the calculator doesn't put the base, because if it's base 10, we call it a common log. Log 5. All right, so log 4, log 5, and the answer is, I'm going to say approximately 0.86. It's close enough for our purposes, 0.86. So now I am down here. Okay, so this is x minus 2x times 0.86 equals 3 times 0.86 plus 2. So let's see what we have here. So I have to do 3 times 0.86 plus 2. 3 times 0.86 plus 2. So 4.58. 4.58. And then I have to do 2 times 0.86. 2 times 0.86. 1.72. So x minus 1.72x equals the 4.58. So 1 minus 1.72 is minus 0.72x. equals 4.58. So now all I have to do is divide both sides by negative 0.72. And let's see what we have. We have x equals, so I have to divide 4.58. 4.58 divided by 0.72, which is 6.36, approximately with the minus, right? So positive divided by a minus is negative. So 6.36, 6.36. And that is my final answer. Okay, so these two are probably the more complicated one when the bases cannot be turned into each other. And the example 4 case is the most difficult because you have different bases and exponent on both sides of the equation. So you have to pick one particular base and take the log using that base of both sides. So as you can see, it takes a while to get the answer out, but it's not really impossible to do. It just requires that we use this technique and use the change base formula to get an approximate value for the expression that's going to be kind of a mixed log with a different base and a different kind of log they're not comparable. Okay, so this is how you solve these exponential equations. We saw all three types when the bases are the same, when the bases can be made the same, and these last two examples, 3 and 4, when the bases cannot be made the same.